Hello there. It seems that when people start to get interested in a dog population in a quantitative way, one of the first questions they ask is how many of them are there? It always goes there at an early stage. Despite all of the metrics we've heard about in previous talks that can be used to characterize a dog population, there is this really disproportionate interest and focus upon population size estimates. And I don't think that focus is going to go away. So with that in mind, and considering that population size estimates do serve an important function despite all of their propensity to involve estimation errors, it really behooves us to think very hard about how we can make these estimates as reliable as they can possibly be, since they're going to be with us for the foreseeable future. Most of what I'm going to discuss deals primarily with free-roaming dog populations, regardless of whether they're comprised of owned or unowned dogs in various proportions, but in principle it applies for the most part to the problem of estimating population size for owned and confined dogs as well. The topic of population size estimation is a very large one. It's much larger than could conceivably be covered in a short talk. So what I've chosen to do is pull out a few bullet points that I find interesting or potentially informative to focus on to just give you a taste of all of this. The first two of them that are listed as goals of the talk are conceptually quite simple, but they're perhaps underappreciated, at least in some quarters, so I think it's very much worth emphasizing them. That includes distinguishing between and defining the two main categories of abundance metrics that we could conceivably pursue when we're thinking about populations and how dense or how many there are. And the second has to do with taking those two categories and sort of comparing the appropriate applicability of them to different applied questions and settings, and making clear that population size estimates aren't the entire answer to the questions that are really underlying those that are ostensibly being asked. The final goal is one that, depending on how I'm doing with time, I may indulge in a little bit of esoterica about some topics that we might consider pursuing in greater detail if we really want to make population size estimates as good as they can be. That gets into the weeds a little bit, as we say in some places in the States, but if time allows, I'll talk a little bit about that, and I will wind up by introducing some ideas about how we could perhaps, hopefully, make population size estimation an easier process by relying on certain kinds of proxy variables. So by going over all of this, what I hope will occur by the end of the talk is that those of you who are in a position to try and determine what sort of metrics you would like to gather for your programs will have a little bit better appreciation of the pros and cons of going down the population size estimation road, and the sensitivity to population size estimates, the issues of standardization and procedure and study design. And finally, for that subset of you who find this sort of thing really interesting from a technical point of view, I'd like to encourage you to find ways to talk with each other about it, to put various brains together and try to come up with the formulas that work the best when pursuing population size estimates for dogs in particular. So, with regard to estimators of abundance, or which are really the fundamental currency of monitoring and survey programs, there are two families of those sorts of abundance estimators: the relative estimators and the so-called absolute estimators. And they differ from one another in that the relative estimators make no attempt, they do not purport in any way to tell you how many dogs really are in the area of interest. They go about it from a different angle, whereas the absolute approach does very much purport to try to give the best possible answer to how many dogs are present within your area of interest. Looking at that in a little more detail, relative, they're usually called indicators of abundance or relative indices of abundance, rely on taking the number of dogs that are counted according to some protocol, keeping those numbers as is, but then standardizing them according to some sort of denominator indicating effort. So the most common is probably to take number of dogs counted per kilometer of road, Same principle. You could standardize by hour of effort, or you could standardize by the surveying of an entire prescribed route. In contrast, so those counts of dogs, and this is an important point, you don't do anything with those numbers other than to standardize them based on effort. When you're going for an absolute abundance estimator, you are doing just that. You're making an estimate, and that requires you to take those raw counts and do something with them, to do something mathematical with them, which we'll talk a little bit more about in a minute. And in the process of doing those mathematical things to those numbers, you introduce the possibility of making errors. Now, any of these abundance indices or estimators can also be then easily transformed into other attributes of interest as long as your survey protocol allows for it, such as the percent sterilized, the percent undernourished, on and on down the line. As a little sidebar of marginal interest, perhaps, to folks in the room, this whole debate's too strong a word, but this whole sort of balancing act between whether you go down a relative or an absolute pathway when you deal with population abundance has got a long and storied history in wildlife science, with different camps gaining sway over different periods of time. So it's interesting to see it now sort of reconfiguring itself to an extent in the world of dogs. So what are the appropriate uses of these two different families of abundance metrics? When it comes to very fundamental things like trends in your population, whether it's changing over time, course corrections, or more formally put, adaptive management, in other words, gaining information as your program proceeds that allows you to make refinements in your implementation, or when it comes to impact assessment, which is basically determined by some combination of trends and some combination of changes in other attributes. All of those things can not only be adequately addressed by relative metrics of abundance, but they're most appropriately addressed by relative metrics of abundance. It's really inefficient, at the very least, to try and address these sorts of questions with absolute abundance metrics. So what that tells us, and a very important lesson, is that the relative metrics of abundance are truly the fundamental currency of monitoring programs, and that shouldn't be lost in the interest that exists with regard to absolute population size estimates. Population size estimates should be regarded as optional but potentially useful, particularly for strategic planning. So if you're working on a large program, for instance, it can be very useful to, if you're thinking about setting reasonable goals, if you're thinking about trying to create a budget that's sufficient for meeting those goals, if you're thinking about what a timeline is that's appropriate for meeting those goals, it's helpful to know how many dogs you're dealing with, at least within the realm of approximation error. And another important purpose that population size estimates can serve is to correct misperceptions. Oftentimes, in the absence of a good population size estimate, a poor one gains currency and becomes sort of the established reality. And in the worst case, those misperceptions can have strong consequences for how an implementation is thought to be best pursued. So sometimes we need to correct misinformation with an estimate. The good news, if we decide to go down the road of population size estimation, is that there's a wealth of precedent and lessons from the field of wildlife science, a lot of it from my own field of avian ecology. This map is just one example of a continent-wide approach to estimating population size for birds by different regions. And those lessons can be sort of distilled down into a set of best practices or critical design elements. Those include ensuring that you are conducting representative sampling, meaning that the samples you draw from the system of interest actually represent that system in a reasonable way without bias. That usually requires us to do something called stratifying our samples, which is beyond the scope of this talk, but it's nevertheless very important. It usually, depending on the method we use, requires us to deal with a complexity called detectability, and that simply means that when you count dogs or anything, by most methods, you don't see all of them. You miss some of them. How many you miss is an important thing to consider if you're trying to correct for that inadequacy in your population size estimate. In the world of birds, we usually address that by doing something called double sampling. So this is just an example of how that works. Somebody has initially stood in the center of this square and done the quick and dirty way of counting birds with something called a point count, but they know they missed some of those birds. What we do then, at least in a few places, is to send somebody back to do an intensive sort of survey of the area, which we call in the bird world an area search. And this involves actually finding every breeding bird that's present. And if we do that in a few places, we can get a good picture of how many birds we're missing when we do the quick and dirty standard point count. And at that point, we can stop doing this intensive stuff and just go out all over the landscape and do these quick and dirty counts, but correct all of them for their inherent detectability. And if we're going to do good population size estimates for dogs, in all likelihood, in most cases, we're going to have to correct in some fashion for detectability. Sometimes that's just not done at all. We also similarly will have to make corrections for the thoroughness of our survey coverage within the sampled areas. And finally, we have to take the information we collect and make the corrections, but then extrapolate it properly to our landscape, usually within the same stratification scheme that we used to design the survey in the first place. So those are the fundamentals, and if any of those get missed, which they sometimes do, you can end up with a holy mess. Some of you are probably familiar with the competing dog estimates for the city of Detroit, which vary by, I think, a factor of more than 10. And in the cases of the ones, and I won't point out the ones that are the most suspect, but in the case of the ones that are the most suspect, generally one of those fundamental premises I talked about earlier has been ignored or improperly implemented or something along those lines. And these aren't just kind of academic exercises. They do have consequences for the decision-making process and for the implementation of programs and the distribution of funding and all of these important things. So there are negative consequences. In terms of cats, some stuff I've been involved in Maui, there's actually an entirely preposterous estimate for the number of cats roaming around the island that's floating around out there and has a certain amount of traction. And because no effort's been made to create a better estimate, it seems to be the one that sticks to the wall, so to speak. And people debate policy based on this kind of number. So we should definitely try to do better than that. And assuming we can, assuming we do those basics and do better than they've done in the previous slide, we still have some slop in our population size estimates. And if we want to get better yet with our estimates, we have to start addressing things that are a little bit more complicated. And I'm going to talk a little bit about some of those. I may skip a slide or two depending on how I start doing on time, but this involves thinking a little bit more about one of the standard tools of dog population surveys, which are mark resite estimates. Many of you know about those. Those are the typical intensive method that's used in a double counting scheme, like I talked about with birds earlier. To work as well as they can, the assumptions that are inherent in this method have to be met, and to the best of my knowledge, we don't really know exactly how well those methods are being met when we use mark recapture or mark recite surveys in dogs. Additionally, there's a certain amount of lack of standardization in how those are implemented that may or may not have some impact on the on how they impact our population size estimates that they contribute towards. We can conceivably do a better job of understanding how detectability rules can best be found and implemented across our landscape in different environments. Oftentimes we just make a best guess at detectability or do a very rough measurement of it and then assume that's good, but we could conceivably do better by understanding how detectability does vary, how the effective area that we're sampling when we do a survey might impact detectability, and even perhaps the effect of survey route configuration and geometry on detectability. So I'll show a slide in a moment that sort of gets at this from a more graphical point of view. Those are some things we could do to make population size estimates more reliable in the traditional sense of actually going out and surveying dogs. But ideally, we could get to a point where we didn't have to go to all of that trouble and dispense with some of that nonsense and just find more easily measured indicators of dog population size. Here we're generally talking about the capability of metrics of human population density to serve as proxy variables for dog population density. And there's probably some real potential here if we do some better meta-analysis of data sets that are currently out there on the landscape. So let me give you a couple of examples of the kinds of things I'm talking about with some of these potential improvements. When it comes to mark recite surveys, we'll typically go down a road, mark some dogs that are in red here, and then go back the next day and see some mix of marked red dogs and unmarked green dogs. The question then arises, or can arise, it doesn't necessarily arise, what area are we effectively generating a population size estimate for on either side of this road? Now, this may be a non-issue in many cases. If you were to assume that the available habitat for dogs only set the red card? Okay. We're only to, the roads are the only habitat available to dogs, then it becomes a non-issue. But I think in some rural settings, there might be non-road areas in which dogs are located. So we need to think harder about the area that we're creating these population size estimates for. And since I am getting up on time and missed the yellow card, let me just go to the human-dog relationship part, which I think is really one of the most interesting, and apologize for the fact that this slide is labeled typical relationship when I realized after I put it together that this is not the most typical depiction of the relationship I'm talking about. But in short, as human population density increases, dog population density also tends to increase, but at a significantly slower pace. In other words, the per capita presence of dogs from a human perspective goes down as human density increases. And there seems to be some regularity to this shape. So even though this curve is a little bit misleading, the typical relationship would have a slightly rising curve, but it would have a slope of less than 1 in mathematical terms. The question becomes, how regular is that relationship and how can it be used to predict how many dogs there should be in an area based on how many people there are? The kind of complexity we need to address to really answer this question has to do with spatial scale, which is a big topic in ecology. So this is the final complicated slide that I'll show. This set of squares are color-coded by human density, with the redder squares having more people in them and the yellower squares having fewer people. You can see here we have a city. You can see here we have a village. Within this square, this little square right there, the human density is about the same as it is within this village. So the question is, are dogs responding to human density at this scale? Should there be as many dogs in this little square as in this little square? Are they responding to human density within the overall settlement? The fact that there's fewer people in this village than in this city. If we answer that question reasonably well, we can start to figure out what the best predictors are of dog population size. And I think there's really some potential here to do a short circuit on that whole complicated process that I described earlier, but time will tell. So that's the kind of thing we're looking into a bit. So wrap it up real fast. Some concluding comments. The relative population metrics are the most fundamental ones, and we should never let our interest in population size estimates sort of overshadow that reality. We should remember that repeating a standardized monitoring scheme using a relative density metric at periodic intervals is really an important and oftentimes underutilized tool for maximizing our management effort and learning from the process as we go along in that adaptive management loop. Remember that population size estimates can be useful, but they have a number of caveats attached to them and they should be interpreted cautiously. With proper analysis, generating dog population estimates can be improved incrementally if we better investigate some of these complexities and if we make sure that all of the basics are lined up properly and in place. And then finally, I think the day may come when we can start to substitute some of this more involved stuff with these human proxy variables if we get more data sets and understand better what the shape that these relationships take. So that will be it for now, and I don't know if there's any time for questions. Okay.
We've got time for a couple of questions.
Oh God, I'm not talking.
Tippy toes.
Oh, hello. Hi, John. That was wonderful. I mean, I love dog population estimates, so I would say that, wouldn't I? There was one thing you said in the beginning that I just wanted to highlight and get your thoughts on. You talked about a dog population estimate for a defined area. And in my experience, that defined area thing is a real problem. So, for example, I've worked a bit in Jaipur with Jack Rees and Helping Suffering, and Jaipur grew by, I think it was 50% over 10 years. So Helping Suffering managed to reduce dog density, and very successful project in general. But because the city grew, the total dog population size grew. Now that wasn't them failing, that was the city growth overtaking their ability to work on a space that huge. The density had gone down, but the city had grown, so the total dog population had increased. But it's not a failure. Your average Jaipur citizen was bumping into fewer dogs every day because they had reduced density. So I think that defined area thing is kind of tricky, because most people would just say, oh, well, the city of Jaipur, that's my defined area, but that is going to change over time.
Well, that's a good example of how the appropriate metric to use to depict change, or change that may be a result of management, isn't that absolute metric, it's the relative one. So regardless of whether the city grew, the relative metrics wouldn't be affected by that. That standardized relative metric would show a decline if in fact there was a decline in density, and the overall number of dogs in the city would change, but you've changed the context of that overall population size estimate too over time, so it would be an apples and oranges sort of comparison.
Any other questions? Okay, in that case, just want to say thank you, John, and to all other speakers today for very thought-provoking presentations on a complex and challenging issue. Thank you all.